Okay, well, we've got enough seats here. Let's see. There's one there. Just right there, yeah.
Come on in.
Oh, no, I'm not.
Okay.
Thank you.
One there too. Okay, well, good afternoon here. Good morning in Utah. Welcome to GIS and Water Resources for the fall 2018 session. Are you excited to be here? Yeah, we're excited to be here.
Woohoo, yes.
All right. And let me introduce my colleague, Dr. David Tarboton. He's from Utah State University. Do you want to say a few words, David?
Good afternoon. It's great to be here, and we've done this together for about 19 years, so this is a lot of fun, and I'm excited to be doing it yet again.
So if you wonder where we're from, I'm originally from New Zealand. Dr. Tarboton's originally from South Africa. You may know there's a foot rugby rivalry between New Zealand and South Africa, so
We're often on the losing end of lately.
yeah, that's true. But anyway, it was, yeah, especially in the old days, it was kind of a nation-defining moment when New Zealand played South Africa in rugby. Okay, so
There you can see we've got a class of about 10 students here that you
Okay.
should see the video of. So I'll switch back and forth between me and them,
okay,
depending on who's talking.
we can see you there. So hello there to Utah State University. It's a beautiful campus that they have in Logan. I've been there several times. Here, why don't you let's just see. Okay, so we're pretty tight for space here, as you can see. In fact, I'm not sure we've got enough seats. So,
There's some empty chairs here.
yeah. And there's a couple of people that haven't been able to sign up to class that I said, hey, just come and see what's going on. If you, as you go through the class, decide this isn't for you, please drop quickly. We've got a waiting list of people who want to come in. So I want to try to have them be able to participate if possible. So I sent around an email with the curriculum in it, the syllabus. I'll just go through this quickly. We've got a set of objectives here about how to manipulate geographic information, which we'll go through as we talk about the exercises that you're going to do in the class. We both maintain a course website here at UT Austin and at Utah State University. Whoops, we're completely out of chairs now. Well, let's see. Yeah. Perhaps you could go look around in the room next door and get one. Yeah. And we maintain a website here at UT Austin, and Utah State University does as well, and we present all the information on the website. There are 5 in-class exercises here. And there's a term project, and there's a discussion here about objectives of the term project and the steps involved in carrying it out. And we're going to have a term project proposal on Thursday, September the 20th. There's a progress report later in October, and then you have to do an oral presentation near the end of the semester. Okay, thanks. Sorry to be short of seats here. We're going to use ArcGIS Pro version 2.2 in this class, and we'll provide the software to you to run on your computer if you want to do that. You can also run it in our computer labs here if you don't want to run it on your own computer. We'll give you handouts and links to the web for reading for the class. We'll also provide the copies of the slides as you've received for class today. The credit is divided into homework 20%, the written report 30%, the oral presentation 10%, the midterm 20%, and the final exam 20%. The final is going to be a take-home. You won't, once the class is closed, if you have to go to Timbuktu or somewhere, well, you can do that, but you have to turn in your homework, your final electronically. The term project is due on the last day of class, so there's 2 things that have to be turned in right at the end of the semester. We're going to have this distribution for the course grades, the plus-minus system, that's standard. There's some stuff here about course instructor evaluations and students with disabilities and add drops and so on. This is the class schedule, and I'm going to go through this in some detail with the slides, so I won't go through that here. I'm going to teach for quite a while. Oh my goodness, or even more. Yeah. How did we get so many? I mean, how many chairs have we got in this classroom? Yeah, I'm sorry, I just don't know. Yeah. Well, I guess if you're not signed up, yeah, you better not come to class. That's pretty obvious here. So, if you want to drop the class, please do. So I'm going to teach the first section of the class, as you can see here. Then Dr. Tarboton is going to take over for a while. Then around the time of the midterm, we'll each do some lectures, and then we'll have a series of lectures after that, and then the term project presentations will start. Okay, so that's the synopsis, the syllabus. Are there any questions about that? Dr. Tarboton, do you want to add anything?
Nothing to add here. Do you guys have any questions though?
Okay, so we're going to have... I'm sorry?
You lost one on that side.
Okay, so one person disappeared. Okay, sorry about that. Okay, so what we're going to do is four things here. We're going to present an overview of the course. We're going to create water knowledge. We're going to talk about what is GIS, and we're going to deal with some basic material about the shape of the Earth. So first of all, an overview of the course. So this might be a new experience for you. Who's been in a video class before? Okay, we've got some here. So we've been doing this together for a long time now. Dr. Tarboton at Utah State University and myself here at UT Austin. And it's been a great partnership, and we've enjoyed teaching with one another. And so we've always had this connection with the video, and the technology's become more secure in recent years. It was a little shaky the first few years we did this, but now we teach together, and you'll see that today. So this is a few words about me. I got my engineering degree from the University of Canterbury in Christchurch, New Zealand, actually in 1972. I went back there earlier this spring, and I taught 50 years after I went there as a student. So I came in February of 1968 as a freshman, and I went in February of 2018 as a professor. So it was kind of a closing of the circle there. I got my master's and PhD at the University of Illinois, and I came here as an assistant professor in 1981. So I've been here however many years that is. I started this class in 1991, and I've been working with Esri on a pre-conference seminar for GIS and water resources since 1994. And there's an organization called the QUASI, Consortium of Universities for the Advancement of Hydrologic Science, and I was the leader of the Hydrologic Information System project of that. That's about 125 US universities that work together to advance hydrologic science. So, and Dr. Tarboton is now effectively the leader of that activity. So, you want to introduce yourself, David?
Sure. So I grew up in South Africa and did my undergraduate at the University of Natal in Durban, right on the beach. So we'd come to class in sandals with sand between our toes. Then I went to MIT and did a master's and PhD and joined the faculty here in 1990. One of the areas I've worked on is digital elevation model analysis, and you'll see some of that work in the TAUDEM software that we'll work with. That kind of is what got me into thinking and being interested in GIS. We've done this class since 1999, so the first, I guess, from 91 to 99 was just Texas, and then it became a sort of online class. And I do research on lots of things related to hydrology, snow, energy balance, stochastic stream flow, physically based modeling. And I've been leading the development of HYDROSHARE. So that's a system that sort of follows on from the quasi hydrologic information system that Dr. Maidment mentioned. And we'll be posting our term projects in that, so you'll get some familiarity with that, and I'll talk more about it later. Thank you.
Okay. So we're going to have these basic elements. We're going to have lectures that like what we're doing right now. We're going to have the video streaming between the two classrooms. We're going to have readings that are assigned web. Whoops, we have another one here. Sorry. Please take a seat. That's all the floors all we've got now. We're going to have homework exercises on the computer and being done by hand. We have a term project that I talked about before, oral presentation, and it's got to be presented in PDF form. And finally, we'll have interaction by email and through discussion and through examinations. So one of the reasons that we want to do this class this way is that traditionally we have a university where once you're in the classroom, you're the only one who knows what's going on. When I was at the University of Illinois as a graduate student, I used to walk down through the quadrangles in the middle of the campus, if you know that campus. And at that time we didn't have air conditioning in many of the buildings, and so they had the windows open. And so you could walk along and you could hear somebody talking about French or history or who knows what. You could kind of get an insight as to what was happening inside the university. And it struck me that that's a nice metaphor, a university without walls, that the community inside and outside the classroom ought to be able to understand what's going on. And obviously you're the ones that are going to benefit from that in the main way, but the intent here in doing the video classroom and posting the videos is to enable people to understand what's going on here who don't necessarily have the time to come here. And the second thing that we want to do a little bit differently is that we would want this to be a community-centered class. And that comes with the last quarter, which is the term project presentations, where we learn from you and you learn from each other. So you've got lots of different backgrounds. It's a wonderful opportunity to learn about lots of subjects that you don't know about yourself. And so instead of just me standing up here or Dr. Tarboton standing up here and just saying, here's what it is, here's the subject, we want you to learn from one another, and that's how we've structured the class. So we're going to do a series of 5 exercises. And this is one that I was just setting up on the class right at the beginning here. And this is the first exercise that we'll start on next week. And it's called Introduction to ArcGIS. And we're going to have a couple of lectures here on introductory material. First about the GIS system, which will be next week, and about GIS and water resources, which I'm doing now. And the goal of this exercise is to understand how to use ArcGIS to prepare a map and a chart and to connect the two things together and prepare a report and turn the report in. So the idea is that after next week you can do what you just see here, and the data are connected between the map and the chart such that these are point observation locations for pan evaporation, and each of these little dots represents an annual pan evaporation. The horizontal axis is the longitude and the vertical axis is the annual evaporation. Among other things, you'll see that pan evaporation, which is evaporation from an open steel pan, increases as you go west in Texas, which if you think about it, it's kind of logical. So when I first taught this course, our goal after the semester was to be able to plot a map. So at the end of the semester, you make a map after 4 months. So the goal here is to be able to do that after the first week. And just sort of accelerate the process a little bit. Yeah. The second exercise that we're going to do is called Building a Base Map. And so the intent here is to say we want to take a particular area, and it's the San Marcos Basin, which is just south of Austin here, and to look at different data sources for GIS and water resources, and also how you express data in spatial coordinate systems, and then build a database for a particular area. And this is, and according to a set of thematic layers. So the thing that makes GIS, or the way that information is organized in a GIS, is it's done with each different kind of information sorted into a separate layer. So the streams layer that you see here is a particular set of information that just describes where are the streams. These hydrographic points like gauging stations and so on that you'll work on in this exercise are a separate layer. Drainage areas that you'll see in this exercise are also a separate layer. Hydrography means the blue line areas where water flows and also water bodies. Channel information, which we're not going to deal with in this exercise, but we will later on, deals with the shape of the river itself. You've got the surface terrain, you've got land cover, you've got population, all kinds of things that can be described on this basin, and the idea is to take a set of information, build a thematic base map, and answer some basic questions about that. Digital orthophotography is a background layer. What is an orthophotograph? Who's seen an orthophotograph? Yes, what's an orthophotograph?
On the top, like the street, like the view of it from the top.
Yes, so every place is looking straight down. So in other words, normally when you have a photograph taken from an airplane, most of it's oblique angles. Well, orthophotography is organised so that everywhere you're looking straight down. And so digital orthophotography is a very good way of getting a sense of, where... Oh, look, here's some more cheers. Thank you so much. Let's hope we don't have a fire here. The third exercise is for spatial analysis. And this is Dr. Tarboton's exercise. Do you want to discuss this one, David?
Sure. So once we start moving to spatial analysis, we're dealing with things like surfaces that are often used in hydrology and water resources. And this exercise looks at the rainfall surface as well as the topographic surface over a watershed. So we'll do things like averaging the rainfall over the watershed and over the sub-watersheds that it's broken into. We'll do things like calculating the slope of the topography and computing things like the average slope. And we'll learn, you'll see there's a little thing at the bottom right called Model Builder. You can actually write programs with ArcGIS that are sort of visual. You can drop a process onto the screen and then connect it to another process and build a flowchart and then push run and it goes. So we'll cover that in that exercise. So the next one, I think that's mine too. So this gets really close to my heart. It's watershed and stream network delineation, because this is actually some of the work that I started working on with my PhD, and I guess we spoke about producing a map from 4 months to 1 week. Well, what I did a PhD on, now you can push a few buttons and get the same results. So, but the idea is that from a representation of the topography, you can identify in a grid cell that water from this grid cell flows to that grid cell and flows to that grid cell, and link them all together and identify all of the grid cells that drain to a designated outlet that provides the watershed. And you can use various thresholding to map the streams, and this exercise will focus on that.
And this is the watershed of?
This is the Logan River.
Yeah.
So I guess you'll be learning a little bit about the geography of Texas as well as the geography of the Bear River Range. The green dot at the bottom left there is right at the mouth of the outlet to the Logan River, just above First Dam for those students here, and we might show a few pictures to introduce the Texas students to First Dam later on. And where we are is just a little bit to the left or to the west of that dot right now. So, go ahead.
Yeah. So then we're going to have a midterm exam, and I'm going to talk a little bit about the National Water Model while you complete exercise 4. We're going to have a review session for the midterm exam, and we're going to pass out a review sheet that will look like this, that classifies all of the material that you've covered in the class up to this time. And the point of the midterm exam is that you should understand, have knowledge and comprehension of concepts and application and analysis calculations. And what that means is level 1 in this taxonomy, Bloom's taxonomy. Who's heard of Bloom's taxonomy? Okay, there you go. Yeah, this is now used for the ABET accreditation for engineering programs. They have to classify everything. My wife did a degree in science education, so I learned this from her, and I've been using it throughout my academic career. So knowledge just means definitions, facts, and formulas, like, what is latitude or something. Comprehension means being able to explain them. What does that mean? Define and explain something. Draw a diagram. So this is just basic conceptual information. Austin is the capital of Texas. That means the state legislature meets here, and so on. Then we have application and analysis. Application means being able to do plug and chug with a formula, convert data from degrees, minutes and seconds to decimal degrees. I mean, analysis means, oh, I've got a whole series of things I've got to do here, and I've got to sort out a sequence and do a whole set of calculations. So the midterm exam goes to level 4 in this taxonomy. So it covers knowledge, comprehension, application and analysis, and that's it. And then synthesis is what you do in your term project. In other words, you're drawing together new knowledge and bringing together understanding of an area that you didn't have before. And evaluation is what we're going to do in the final exam. So you compare and contrast alternative approaches. That's the highest level of abstraction in this class. And that's how we're going to structure the different pieces such that you've reached a certain level of competence by the time of the midterm, and you've hopefully got a higher level of understanding by the time we get to the end of the semester. We will also, for the midterm, lay out a set of expected skills that we expect you to be able to do. In other words, you don't have a computer, you're going to be sitting here in the classroom, so you've got to be able to just write things out by hand. We'll give you some homework exercises that involve doing things by hand as well as by computer so that you can prepare yourself for that. Obviously, you're going to need to be able to bring a calculator and use a calculator in the classroom because we won't have the software here for you to have access to. So we have this pretty well prepared. We post the exams that we've done in the past so you can see what's going on. It's not going to be a surprise, so don't get into an agony like, oh my gosh, I don't know what they're going to ask on this exam. And that's going to be on Tuesday, October the 16th. Then we're going to follow that with exercise 5, Dr. Tarboton.
So this is a really interesting idea that has sort of come to our consciousness over the last 3 or 4 years, referred to as hydrologists drainage. One of the things that you can do with a digital elevation model, as you think of the process of flowing from each grid cell downhill to the next one, you can see when you hit a stream, you can look at the elevation in the stream, the elevation where you started, and that is the height you are above the stream. Now, if there's a flood coming down the stream, and the depth of water in the stream is more than the height that you are above the stream, you're likely to get flooded. So this idea had emerged in the literature probably 7, 8, maybe 10 years ago. But when Dr. Madman was working on the sort of national water model and some of the ideas for trying to figure out how to take discharge results the national water model was producing and map them into flood inundation, we sort of picked up on and rejuvenated this idea, used it, found one of the TAUDEM tools was actually able to calculate the distance to the stream in any sense. So you could calculate the distance to the stream in the vertical sense, which became this quantity. So this exercise, you'll actually work with that. There's actually another thing you can do with that is you can also calculate the hydraulic properties of the stream. If you think of, if you've got a stream and you fill up with water, it spreads out. Over a certain length of the reach, you end up quantifying the volume, and if you divide that by the length of the reach, you get the cross-sectional area, and volume and cross-sectional area, as it increases, you can also get the wetted perimeter, and those are some of the hydraulic properties that we need for routing flow downstreams. So this exercise will give those ideas to you.
So I put here these two functions, flow direction and flow distance, and so one thing that's really cool is that Esri has adopted the approach that Dr. Tarboton was describing and has embedded it into the core software of ArcGIS. So this thing that says here, D-infinity flow direction type, is Dr. Tarboton's PhD dissertation. He was the one who invented that concept, and he'll talk about that when we get to that part of the lecture. And then this vertical flow distance means how high am I above the bottom of the creek. So in 2014 we started building or working on the national water model here in Austin, and in 2015 we got it going, and we produced a first draft of being able to run the flow calculations for the whole country, on all the rivers and streams in the country. But then after that came the question, how do we translate flow into inundation? So while we were teaching this class 3 years ago, fall of 15, we were discussing back and forth between ourselves about how to do that, and we got it figured out. And so now you're going to be able to do the encapsulated version in the ArcGIS software, and we built a system for flood inundation mapping for the whole country, which the National Weather Service has adopted. So these points that you see here are address points. So we here in Austin UT Austin have collected together all the address points of all the locations in Texas. So when you call for an ambulance and they say go there, that means the dispatcher can see a dot on your house. You don't know there's a dot there, but there is. And so police, fire, whatever, they go to dots. In Travis County here, there are 355,000 of these dots. So we run around all the counties in the state and collected them together. Then when we have the inundation mapping, we can count how many people were being flooded. And this time 1 year ago, we were doing that, and it was Harvey. Hurricane Harvey was going on at this particular time. So actually it's a lot easier to prepare for this class without having a hurricane going on. This crazy period. So the last part of the class is presented here. We're going to have some additional lectures for a couple of weeks while you after exercise 5, and then there's going to be a long session here of 10 project presentations from Texas and Utah. We'll choose the order of presentation of this randomly, so we'll have groups of presentations, and then you'll come and just choose a date. A whole group of people are going to get a date. Some people are going to be winners and get dates right near the beginning to show how good they are. Some people are going to be losers and get dates near the end, which means they'll have more time to work on their projects. But in any case, I bring this to your attention now because it means don't delay getting started on your term project. So the proposal's due on September the 20th, the report's due on the 23rd of October, and then the presentations start on November the 13th. Don't leave it this late before you get started on the work, because otherwise you just don't have enough time to really bring something together. It's better to work away at something steadily during the semester. Don't leave it right to the end. So first, let's talk a little bit about how we create water knowledge. And I think of 4 basic water problems. We have too much water, that's a flood. Not enough water, that's a drought. Dirty water, that's water pollution. And we have ecological degradation, where we have lack of capacity to support fish and wildlife. Now, we need a framework for all of these. We want something that will be good for floods and good for droughts and good for water quality and good for ecological protection. And quite a few years ago, I worked on this book, Handbook of Hydrology. Actually, I worked on, I gave 4 years of my life to doing this. And it was a compendium of hydrology of all areas of knowledge. There are 58 authors and 29 chapters and everything you can think of. And at the end of that experience, I thought to myself, how was the knowledge in this book created? That's actually a pretty important question. How do you create knowledge? I mean, we spent 4 years putting it together. Where did it come from? And I concluded that there are 3 ways in which knowledge is created. The first is by deduction from existing knowledge. I mean, I know this already, I can then infer that with a reasoning process. The second is by experiment in a laboratory, and we have lots of classes in our program that deal with lab kind of work. And the third is by observation of the natural environment. And I don't think there are 23 ways that things are discovered. In my opinion, this is the 3 ways that things are discovered. And I want to give some examples of that. Firstly, of deduction. This is the Principia of Newton. Who's read the Principia? Oh gosh, I mean, you guys have missed out on a bestseller. So, Newton wrote in Latin, but it's been translated into English. This is my copy of the Principia. And this is what Newton wrote in May of 1686, that the ancients divided mechanics into 2 parts. The rational, which proceeds accurately by demonstration, and the practical. It occurs that mechanics is so distinguished from geometry that what is perfectly accurate is called geometrical, and what is less so is called mechanical. Yet the errors do not come from the art, but from those who practice the art. In this sense, rational mechanics will be the science of motions resulting from any forces whatsoever, and of the forces required to produce any motions accurately proposed and demonstrated. So what Newton did was he took geometry and he used it to establish a precise science of mechanics, of forces and motions. And that underlies everything that we do in engineering about, rockets and water flow and all of that. So he made precise what was formerly fuzzy. Very squared away, right, this is black and white, very clear. So we can say that what Newton did was the classical path of mathematical physics. given a set of axioms, then by a logical process derive a new principle or equation. Now I want to suggest that computer modeling, as we currently practice it, is a kind of current modern equivalent of that. Given a set of input data, then using an algorithm, derive a computational result. And this is the National Water Model. This is the version that we used for the setup in 2015. It calculates the flows in 5.2 million kilometres of rivers and streams in the nation, and it went operational at the Weather and Climate Operational Supercomputer System in Washington in August of 2016. So this is now the nation's system for forecasting water, and there's a piece of the nation's weather forecasting system that's devoted to water that runs the National Water Model. An experiment, to me the greatest of all the experimenters is Louis Pasteur. And what he did was, he was a laboratory person completely. He replicated the real world in a simplified way under controlled conditions. And what Pasteur did was he showed that microorganisms cause disease. He was the first person who did that. He was actually a biologist, not a doctor. And he discovered the concept of vaccination that was invented by him, that you build up the dose inside of an animal, you draw the blood from the animal, you put it in the human acquires the immunity that the animal created. And that's the foundation of scientific medicine. My wife and daughter are both doctors, and there's Louis Pasteur Drive. It goes right by the medical centre in San Antonio where they trained. So laboratory experiments are good for microscale rather than the whole world, and so it's really critical for water chemistry and biology. And I just picked out this chart of microorganisms in water, and bacteria and pathogens are the key reason why you do not drink water from creeks. They'll do bad things for you. More length of rivers and streams in the nation is polluted because of microorganisms than for any other reason. Not industrial chemicals, but microorganisms. And finally, for observation, I want to use the example of Charles Darwin. This is The Origin of the Species. Who's read The Origin of the Species? Yay! Okay, there you go. Yes. If you want to, have something to put yourself to sleep with at night, just keep The Origin of the Species by your bed and read a couple of pages, and you've got to really think about it for a while, and then you think, oh no, I'm not going to do this anymore. So he said, when on board the HMS Beagle as a naturalist, I was much struck with certain facts in the distribution of the inhabitants of South America and of the geological relations of the present to the past inhabitants of that continent. These facts seem to me to throw some light on the origin of species, that mystery of mysteries, as it has been called by one of our greatest philosophers. On my return home, it occurred to me in 1837 that something might perhaps be made out of this question by patiently accumulating and reflecting on all sorts of facts which could possibly have any bearing on it. And that was my italicization there. I'm here going to give only the general conclusions at which I have arrived at with a few facts and illustration, but which I hope in most cases will suffice. This book was published on the 24th of November 1859, and it's been called by some the most accessible book of great scientific imagination ever written. And it's still in press. It's amazing that that's the case. But notice the difference here. This is not precise like Newton, right? This is not squared away at all. This is a lot of uncertainty, a lot of interpretation. This is a different world, but still an important world to be able to create knowledge through observation. And here's a map of water observations in the United States. This is produced every day, and it's kept up throughout the day by the US Geological Survey. And it shows the current flow in about 7,000 gauging stations. And the colours represent how high the flow is relative to its average at that point. So blue means there's high flows, red means there's low flows, and green means it's roughly in the middle. So these things, this data set of observations is crucial. Hydrology, to a large degree, or a significant degree, is the science of observation. And so linking these two things together is important. In fact, this is how the National Water Model works. It links observations and modelling at the continental scale. You cannot do that without an information framework. You can't just say, I'm going to run my program and shove my data in. No, this is a much, much more complicated thing. And it has to have an underlying information framework to make it work. And that's what the Geographic Information System provides. Now, inherent in that is the idea that we're connecting the land and water systems of the nation. So we have river and stream lines that describe where water flows, and we have the land surface topography that's kind of like the yin and yang of that system. One is really the obverse of the other. We're going to talk a lot in this class about spatially discrete features, points, lines, and areas. You either have it here or you don't. And we're going to talk about spatially continuous rasters, in other words, continuous surfaces that exist everywhere. And the duality between one and the other forms really a key piece at the heart of what we do in the class and what Dr. Tarboton was talking about when we introduced the exercises. So we need an information framework that can link modelling with observations, with topography, with features and rasters and point observations, and that's what we're going to attempt to do, and that means we have to have some kind of thought models. And so an information framework can be thought of first of all as a conceptual model, have a set of concepts and describe a subject and allow reasoning about it. And Newton wrote in his Principia 3 basic principles, Newton's laws of motion. And I know you're really good at Newton's laws of motion. Yes, Newton's first law of motion. To every object, yep. All right, there you go. Every object will stay at rest, will stay at rest unless the force acted upon it. Actually, I think it's every object has in motion will stay in motion unless it won't change its motion unless it has an external force. Newton's second law of motion. Okay, so we say force equals mass times acceleration. What Newton said was any object that's in motion, if acted upon by an external force, will change its motion in the direction of the force and proportional to the magnitude of that force. That's what Newton said. There were no equal signs. He didn't have algebra, in the same sense that we do. So, and then Newton's third law? Okay, there we are. Go Bangladesh, yes. To every action there's an equal and opposite reaction. Those are the conceptual frameworks that lie behind Newton's Principia. And even though they're stated in words, we've translated them into F equals ma, force equals mass times acceleration. So we've translated that into math, and away we go, and all the things that we do in engineering and science, but they weren't formulated that originally. Newton, although he invented the concept of mass, didn't call it that. He called it quantity of matter. And he invented the concept of momentum, but he didn't call it that. He called it quantity of motion. So in other words, the basic conceptual ideas actually underlie what goes into mathematics. So what we deal with now, we have it all reduced down to symbols and everything like that, but that's not the way it was originally started. Now, what we're doing with data, we can say there's a thing called a data model. What the heck does that mean? It means a conceptual model describing something that's expressed in a data structure. And it can be in anything, ASCII files, Excel tables, or whatever. And a geographic data model, which is what we're going to use in this class, is a conceptual model for describing and reasoning about the world expressed in a GIS database. And that is the foundation for our work here. So it's, when we talk about data models and geographic data models, this is a way of thinking about the world which is derived from concepts just as Newton's laws are, but it describes how things are organised in the world and how they interact with each other. And so a data model is important because the way the information is organised can enhance or inhibit the analysis that can be done. And this, you'll see that as we get into this, that really the way the data is organised is critical. This is a neat guy. His name is Scott Morehouse. He's like kind of a Zen guy. Yeah. He's a friend of mine. I first met him in 1990. I've been going to the Esri User Conference every year since 1990, and I've met Scott in 1990. And he's the intellectual architect of ArcGIS. Now, this behind the scenes, there's a guy. Well, actually, he's nearly retired, and he's like me. He's going up to the pasture. But in the early years, starting about 1980, he was behind the scenes. There's this one person who's just figuring everything out in his head, and this is Scott Morehouse. And he said, all geographic information systems are built using formal models that describe how things are located in space. A formal model is an abstract and well-defined system of concepts. Geographic data model defines the vocabulary for describing and reasoning about the things that are located on the Earth, and geographic data models serve as the foundation on which all geographic information systems are built. So as you work on this, you'll be thinking not just about how do I manipulate data, but about geographic data models and about ways to organise things. So let's turn now to what is GIS. So as a broad definition, a geographic information system is designed to store, capture, manipulate and all that kind of thing. Maps, data, tools, computation. That's a rather grand definition. And key to that is the idea that geography is visualized in maps. So these are some maps of the local area here. Dean Keaton Street is the street just outside of our building, and it's got some attributes here. It's got an address and it's got a zip code and so on. So GIS is not just about where things are in geometry or images, but also providing descriptive information about the objects. Maps are built from data. So in this instance, our building, Cockerell Hall here, for those who are in civil engineering, it's an object. You can see it's a rectangle represented here. It has a name, it has an address, it has a thing called a shape, and that's its geometry. So inside of the GIS, there's a file which you don't get to look into that describes what the shape of something is and where it is on the Earth, and that's called the shape. And it can be a point, it can be a line, it can be an area, it could be a volume, but that's where all the geometry is embedded. And separate from that are the attributes that you see described here. And here are some data that I just drew up around our campus. We have points. In this case, it's Austin Cardiac Services. We have lines for the creeks, and we have polygons for the buildings. So points, lines, and polygons are the three features that we're going to work at. And those are themselves an abstraction of the real world, the raster information that describes the world in terms of very small little pixels. And what's really impressive as we go along is that this information is now much more precise than it used to be. We've got an incredible capacity to be able to image the world in much more precise ways than we could before. Some other kind of raster data, land cover, rainfall, elevation. We're going to look at lots of things as continuous surfaces. And there are some other more abstract data types. Triangulated irregular network is something that uses triangles to be able to formulate things that are more kind of sharp-edged than what rasters can deal with. Multi-patch means sets of triangles that make volumes. And there's annotations that can be describing or things that you can put on maps. And there's actually some other things too, multi-dimensional frameworks. Now this is an important concept, 3 views of GIS. And I've, in the synopsis that I wrote up for today's lecture, let me just go to that. So I've written a synopsis and posted it on the website this morning, and I think Dr. Tarboton posted it also. And so this is a narrative about what did we cover in this lecture. So we want you to say, what was I learning here? Just summarise the basic points. So here's the story you can see at the bottom here about deduction and experiment and observation and all that. And here's another story here about geographic information systems. I thought of as comprising 3 parts. A structured set of data, which is the geodatabase, geovisualization, which is how you look at things on maps and interpret spatial patterns, and geoprocessing, which is a set of transformation tools to get new data sets from existing data sets. So and here's programming, and Dr. Tarboton is the expert on programming, so let me turn over to him here.
So this is just an example of, I guess, part of the geoprocessing aspect of GIS, where once you've got information organized into a data model, you have the system ArcGIS or ArcGIS Pro, the mapping system. You can visualize things. But what if you want to produce an analysis? You want to, say, come up with the area average rainfall for each of the sub-watersheds of a river basin. Sometimes you need a program or a set of tools to do that. We need to be able to link tools together. So I think of programming as providing 2 sets of functionality. One is automation of repetitive tasks. You might be able to do something once with just the tools that are there, do it 2 times, 3 times, 4 times. But now if you have to apply it over the whole country and you're doing it thousands and thousands of times, that's not the sort of thing that you want to be doing as a human. So you need to get a computer to do that. So you need to program to effectively string together the set of instructions, the code, if you will, that does that. The other aspect of programming is if you dream up new behavior that you want to be able to calculate from the data you've got, that you can't find a tool, or a tool doesn't exist in ArcGIS for doing that. For example, prior to the sort of current implementation, we didn't have an easy way in ArcGIS, we didn't have any way at all to calculate the height above the stream. So I ended up doing some programming to set up the Tarboton tools to do that, and now Esri's sort of picked up on the idea. So if you often are being innovative and thinking, well, this is really the physical quantity that I want, there may not be a tool that does it, and you have to get into programming to sort of do that. So those are some of the things, and we'll just scratch the surface of that to sort of show you some of the capability, and maybe if you're interested, you can learn more and take advanced classes, or just learn by yourself is often not a bad thing.
So Dr. Tarboton, I can do this, Dr. Tarboton does that. Yeah.
Not enough of that.
You want to talk about HYDROSHARE, Dave?
Okay, so so this is getting into, we heard the sort of the idea of data models for representing geographic information. If you think of hydrologic information and you want a system to be able to organize that, you think about, okay, what are the sorts of data that hydrologists have to deal with? And you quickly come up with a list of things like time series, a lot of geographic information, things like the geographic rasters and geographic features that are part of GIS that we're dealing with. The time series is typically not part of GIS. GIS is developing capability for that, but that's sort of been late in the evolution of GIS. Multidimensional space-time data, which we often get from the atmospheric sciences, and it's represented using data models that come from that area. And then computer programs that are things like implement the national water model, and then the application of them to a specific location, which is what we call a model instance. So we realized that hydrologists need to work with all of these things, both data and models, and they need to work together. No one person can solve all the problems, so they need to collaborate, and they need a system that they can put things in together. And that's been motivating us and been our vision while we've been developing HYDROSHARE as a place that you can put hydrologic data, you can put hydrologic models that other people can then retrieve and work with. So what's next? So this is just a couple of screenshots from HYDROSHARE on the right, where it sort of shows the steps of you can create data, upload data to HYDROSHARE, describe it with metadata, and share it with your colleagues. It's operated by Kohazi, so it's for the hydrologic research community. It gives you a way to share your data sets. It has a way to support collaboration. It has links to computational resources, because once you've got data in a sort of web-based system, you have the capability to have fairly large data sets, and downloading it and working with it on your computer can sometimes be a bind. It provides permanent publication of data and models with citable digital object identifiers. So some of you have probably heard of a DOI that can link to literature. And all in all, it's really a system to advance the field by helping people work together. And the concept of fair or findable, accessible, interoperable, and reusable is really being pushed by the American Geophysical Union and other journals in terms of opening up data. And HYDROSHARE is trying to participate in that movement, if you will, to effectively support our research and make it transparent by not only sharing the paper, but also sharing the data behind the paper, so other people can reproduce it, other people can build on it.
So this system was inspired by the move of ArcGIS to the web and the system called ArcGIS Online. So I showed the map that you're going to create in exercise 1, and the equivalent process in ArcGIS is to create the map and then to upload it to ArcGIS Online, to describe it with metadata, and then to share it with colleagues or the world. So this is just the same process, so you can go and see how this works as you go along in this class. So HYDROSHARE is kind of system built specifically for hydrology, but it was inspired by the development of ArcGIS Online, which happened starting about 10 years ago.
So that just is an illustration of some of the data that we've got in HYDROSHARE. And this is a project just after Harvey, which Dr. Maidment was intimately involved with, let's say. He said, well, there's been a huge amount of data that was collected. If we can make this available for study, perhaps we can learn from this event, and perhaps we can do a better job of protecting, mitigating in the future. So we wrote a rapid proposal to the National Science Foundation, and rapid proposals are ones that they sort of fund in a hurry. And so it's a little bit shorter than usual. You just have to motivate it to the program officer, and they'll give you some money, in this case, to help collect the data that came out of the Texas Emergency Management Center and organize it so that it's properly described, that others can access it, and put it in HYDROSHARE for people to use and work with. And we're just getting to the point where the Harvey collection is sort of getting to be complete. There's few I's to be dotted and T's to be crossed, but it's largely ready to go.
Okay, so now let's finish the class here by talking a little bit about the shape of the Earth. And ESRI presents itself as a company now about the science of where. I hadn't seen this slogan before this year, but it's now what they say. And this is Jack Dangermond, the president of ESRI, and I sent around some notes so that you can watch the videos of Jack talking at the ESRI user conference. I hope you enjoyed that. I have to say he's the best speaker of this kind that I have ever seen. And if you look at those slides and you see all these little fluffy things and, you know, boxes and things going in all directions, that is not random. It's an incredible amount of time that he puts into preparing those presentations. In fact, I did a talk with him once, and I went out to his office in California to work on it. Actually, it was right after Christmas, and the first day we spent from 10 in the morning till 1:30 in the following morning without any breaks. We never left the room, actually. And Jack's wife would call up and say, "Hey, Jack, you want some lunch?" "Oh, yeah, sure." "Hey, Jack, you want some supper?" "Oh, yeah, sure." And after about 9 o'clock, I'm saying, "Jack, give me a break. I'm degrading here." And he's saying, "David, focus." And then the next day we started at 8 in the morning and we finished about 7 in the evening. So, and that was 26 hours. And at that point we had the first draft of 40 slides after 26 hours. Yeah. And that's only the first draft. Now, then we're going to the conference. I was in the hotel in Dallas, the airport in Dallas, and I get the phone call. "Hey, you were here yet?" "Oh, we got to revise this thing." Give me a break, Jack, you know. I'm still in the plane. But yeah, so you know, Jack's a visionary guy. There's no question about it, and he's built up the whole ArcGIS, you know, as a business, and you know, with Scott Morehouse's help on the design side from the beginning, starting in about 1980. So I mean, he and his wife own the entire company. I read a Forbes list. He's the 527th richest person in the world. Yeah, it's worth about $5 billion. But this is, he's a tremendous visionary, and it's been very inspirational to me in terms of the arc of my professional career. And I've really benefited a great deal by being able to help to add something to their system. And central to the idea of the science of where is how you describe the location on the Earth. And you know, we all have a pretty good idea of something about this. But I found when I first started working in GIS that the thing that I needed to learn that I didn't know was I didn't really know much about geodesy and about the shape of the Earth and so all that. So my wife was training as a kidney specialist at Stanford University Hospital, and I spent about 3 months just holed up in the Earth Science Library, and I read every book I could find about geodesy and GIS and things like that, geographic projections, and I got a feel for it. And here's some just basic ideas. We've got a grid around the Earth. We've got a graticule of coordinates set out on that. We've got 0, 0 here. So 0 latitude means what?
Distance from the equator.
Okay, so that means 0 latitude means the equator. And 0 longitude means what?
Prime meridian.
The prime meridian, which is where? Where does it pass through? Greenwich. Who's seen the prime meridian marker on the ground in Greenwich? Yeah, I have. I've been there. I went to see it. So just outside of London, you take a boat down the Thames and you walk quite a ways from the Thames River and climb up a hill, and there's the observatory at Greenwich, which was actually an astronomical observatory, and you see the mark on the ground which was established, where the prime meridian was established. So we've got, if we go in lines of longitude, those are called meridians, and they range from 180 west to 180 east. And those have been translated into things like the Near East or the Middle East. When we talk about the Middle East, or even the Far East, that's all things that are east of Britain. Well, that was where that nomenclature was established. So all things east are positive in terms of longitude. Everything west of England, which is everything in America, is negative. So all, in terms of decimal longitudes, all longitudes that we deal with will be negative. And that's a trick. You've got to be a little bit careful because of that. Likewise, a line of constant latitude is called a parallel, of which the prime one is the equator, which is 0 degrees latitude, and minus 90 is at the, minus 90 degrees south is at the South Pole, which is minus 90 in latitude. So the southern hemisphere is all negative in latitude, and the northern hemisphere is all positive in latitude. So here in America, we're positive in latitude, negative in longitude. Here's just some fun facts about where are you. 30 degrees, 18 minutes, 22 seconds north, and 97.45, 3 minutes west in Austin, and similarly for Logan. So we can locate ourselves with latitude and longitude, degrees, minutes, and seconds. What is the number base of this system?
60.
It's 60. It's a number base of 60. So that's a very interesting note. This is not decimal anyway. This is much more ancient than the decimal system. So the idea of dividing things into groups of 60 is a very ancient thing. It comes from Mesopotamia, actually. What other thing do we deal with that's base 60? Time, yeah. 60 seconds in a minute, 60 minutes in an hour. So time and space have this really interesting numerical system. Base 60, not base 10. And here's some other things that are sort of interesting. If you look at the United States, 60 west to 120 west approximately bounds the country. So that's 60 degrees out of 360 if you go around. So the US is about 1/6. If you take a slice out of the world, about 1/6, and you like eating an orange or something, that's big enough to capture the United States. Now, one of the things that we're going to use a lot here is the idea of map projection. The concept that we take a curved Earth and we flatten it out, and so it becomes a flat map. So when we get to engineering and science, you've been accustomed to working in XY coordinates. I mean, that's everything we do is in XY coordinates, dy dx, dz dx, and so on. And these are called easting and northing coordinates. And there are many of these coordinate systems. And we'll learn something about those in a lecture the week after next. But the Earth is not flat, it's curved. And so the geographic coordinates are latitude and longitude, and they're called phi and lambda. So you may not be familiar with phi and lambda like you are with x and y, but that's what they are. Now, something that's a little bit misleading is that when we talk about latitude and longitude, phi is up and lambda is across. So it's like yx, not xy. So this is what goes up and that is what goes across. It's sort of the reverse of when you think about x and y. Now, as you do a transformation like this, you take a curved Earth and you make a flat map. Can you do that with perfect fidelity? No, you can't, right? It's not possible to make a curved surface into a flat surface. So the way that this is done has preserved certain properties of the shapes and distances and areas. And so particular transformations that we're going to use are chosen so that they, among other things, preserve area, because if you can have, well, the distortion in this direction is just the inverse of the distortion in that direction, that means the area comes out being okay, and that's important for hydrology. So we use equal area projections for that reason. Now when you do this Earth to globe to map, there's two steps involved. The first is we want to take the Earth and reduce it down to a small version of itself, like Earth to globe. And that involves a ratio that's called the representative fraction. And actually, while I was messing around on the computer with the project at the beginning of class, I was actually changing the scale. I was changing the representative fraction, and the map was coming back and forth as I did that. And that means the globe distance divided by the Earth distance. And 1 to 24,000 is a really important representative fraction. Why is that? So has anybody seen a USGS topographic map? Oh, one person. Oh yeah, we got some USGS topographic maps. I should really get one and bring it to class, because for a long time, paper topographic maps were the basic way that we located ourselves on the Earth. And the basic set of USGS topographic maps for the United States has a scale of 1 inch to 2,000 feet. And if you think about 2,000 feet times 12 inches, that's 1 inch becomes 24,000 inches. So this 1 to 24,000 means 1 inch on the globe is 2,000 feet on the Earth. And that's the basic map scale that National Information was compiled. Now, as you flatten out the globe and make it a flat map, there's another distortion involved. And so the actual distance compared to the globe distance has a fraction that's nearly 1 but not exactly equal to 1. So different places on the map, that factor can be defined. Now, as we're doing this, what we're going to do is to take a set of coordinates that are in what are called geographic coordinates on the Earth's surface, and we're going to make them into a set of projected coordinates on the map. And the origin of the coordinate system on the Earth's surface is called phi 0 lambda 0. It's the reference latitude and the reference longitude. And then there's an equivalent point on the Earth which is called x0, y0, and that's called a false easting and a false northing. Now those numbers you might think should be 0, but often they're not 0 because you don't want to have negative coordinates on a map. So for example, all the mapping for Texas is done with a point down to the southwest somewhere of the state, so that you've got to go across and up, and both x and y will always be positive everywhere in the state. So this number here is actually set up in a somewhat artificial way so that in the area that you're concerned with, you're actually in the upper right quadrant of the map, and all your map coordinates are going to be positive in both x and y. So I think that's it. Yes, so that's the end of our little story here about the shape of the Earth. We're going to come back to that in quite some further detail as we go along in the class. So we've got a few minutes to spare. Are there any questions you have? Yes.
Can you please repeat the last point? How to get the predicted coordinates on the
let me think about this. So let's suppose that this is the universal transverse Mercator system. Right? That's a typical system that's used for military coordination, also for emergency response. What happens there is that the x coordinate is set at minus 500,000, and the y coordinate is set at 0, and the point that you start off with is actually lambda 0, phi 0 lambda 0, and it's on the equator. So if you're in Texas, we're always north of the equator. Therefore, if we say y0, if we say y0 is equal to 0 and we're north of the equator, we're okay because the coordinates will always be positive. However, what the universal transverse Mercator system does is it draws a line down through the middle of the area that you're concerned with, and so you have points on the left and you have points on the right. It's actually in 6-degree strips. So they have 3 degrees to the left and 3 degrees to the right. Now, the reason for making the x0 500,000 is so that, that point which is now in the middle is 500,000. So over here is 0 somewhere, and all the area within those 3-degree band will have positive numbers. And it might be 200,000 or 100,000 or 300,000, something like that. But they'll always be positive, even though they're on the left-hand side of this middle coordinate line. Yeah, and so, for example, for emergency service, for emergency rescue here in the state, we use the Universal Transverse Mercator system, and that's how the aircraft are tasked, and helicopters. And if you go and rescue that person there, they give XY coordinates in the Universal Transverse Mercator system. So if you think about that, you don't want to suddenly get, oh, I got a negative number here. No, they want positive numbers. It's a little bit complicated because if you think about Texas, it's big enough that it's more than 6 degrees gets repeated 3 times actually. So if there's actually 3 different zones over the state, and the East Texas around Houston has a different zone than over the mid-state, and the Western state has a separate one. Any other questions? Dr. Tarboton, any questions from your team in Utah?
Any questions from you guys? Looks like we have a quiet bunch today.
Okay, yes.
I was just curious about when we'll be receiving the software, the software for the work that we'll be doing.
Yeah, so the first thing that I have to do is that I have to send a list of the registered students in the class to the organizational account administrator here at UT Austin, because that's what gives you permission to access the software. And I want to just wait a day or two to do that to get this enrollment stabilized for the class. Then I'll send that list in, and then you'll get an invitation to join the ArcGIS online account, and the same will occur in Utah. And then you'll respond and say, yes, I am who I am, I've got a login and password. And then I'll turn out also a set of instructions for you to download the software and be able to, once you've got that and once you've got your login, then you're good to go. And we're doing the exercise a week from today, so we'll get that done by next week. Yes, any other questions?
For the project,
Uh-huh.
are we going to be doing a river basin in the United States, or can it be somewhere else?
You can be anywhere that you like. So yeah, there are many projects in this class done for overseas locations. And so there's always a section of presentations that deal with international projects. It's a little bit more challenging because getting data is something of an issue, but nevertheless, many successful projects have been done by students who are doing projects overseas. In fact, it's become, because there's more online resources now than there used to be, it's become easier to do that. I taught a class this spring in New Zealand, and there were 2 students from New Guinea. And I said, oh, you can delineate watersheds in New Guinea. And they said, we got no data in New Guinea. I said, yes, there is. You just got to know where to look. And sure enough, yeah, we were able to do that. Okay, any other questions? Yes.
Is this class streamed online as well?
Yes, the videos are going to be, it's not streamed in real time, but the videos are posted after the class is over. And there's a link on the course webpage to where to get them. So let's quit now, and I've got the list of registered students here, and I want to call that out. And I just counted while I was going here. There are only 33 seats here, so we're going to have a discussion about how many seats and how many students, because they've already registered 36. So that's why we've got some seating problems here.
Yes.
Yeah, so let me
Thank
say
you, and
goodbye
we'll
to-
connect again on Tuesday.
Yes, we'll connect again on Tuesday. Thank you very much, David. Okay, so let me call the roll here. And if you've got a name that's not what I'm calling you by, or I'm mispronouncing your name, please let me know. So Shelby Acosta, okay. Katrina Baggerman.
I go by my middle name, Jill.
Jill, okay, thank you, Jill. Whitney Benson. Yes. Emily Bristol. Quining Chen. Qing. I apologise. I've got my cues to be Ting. Okay, Qing. Okay. Andrew Chu. Yes. Carolyn Cooper. Andrew Dennis.
I go by AJ.
AJ. Okay, there you go. AJ.